So this is our third unit, typically the third unit, which is our unit on energy. Our first lesson is going to be on work and kinetic energy. So I have this PowerPoint that I made, and you can access this on our Google site. They're all there. So first of all, types of energy. There's so many different forms of energy. Some you probably already know. Radiant energy. So that's the energy due to light or electromagnetic waves. And you can certainly feel that, especially on a nice day like today if you go outside. Right? Sunny day, you can feel the heat. Right? So there's radiant energy coming from the sun for sure. Kinetic energy is going to be one we're going to focus a lot on. And we're going to learn more about that today. But it's the energy due to an object's motion. So it's the energy behind motion. Potential energy. Now there can be lots of different types of potential energy. I like to think of potential energy more as stored energy because it is there, right? It's not like there could be energy. Right? I don't really like the word potential in that sense. So I think of it as like stored energy. And there's different places that you can store energy in an object, for example, due to its position or its composition. And we're going to go over quite a few. Specifically tomorrow, we're going to go over gravitational potential energy, meaning that an object has more energy the higher up you lift it in a gravitational field. You can certainly visualize that if you were to drop something from 1 meter high and then drop something else from 10 meters high. Right? Drop it from 10 meters high, it picks up more speed because it originally had more stored energy. Elastic potential energy. If any of you have ever stretched and shot an elastic across a room, you know that there's energy stored inside of something that is stretched. An elastic material that is stretched specifically. Chemical energy. That's energy stored within the bonds of molecules, for example. And we're going to talk about that too, right? This is why this unit is so big. Nuclear potential energy. That's energy actually stored in the atom of a nucleus. Electrical potential energy. We'll talk about that more, not in this unit, but we're going to do a whole other unit on electricity that we'll talk more about that in that case. Thermal energy. Right? In a sense, you can almost think of thermal energy as all the kinetic and potential energy inside of particles. But again, we're going to spend a lot of time on thermal energy as well. That's why this unit is so big. And the one that you're all used to, because we actually did waves first, because we had that in class, was sound energy. All right, so starting with the lesson, we're going to talk about work. Work isn't work in the sense in which we use it in the English language. In physics, work is a force that acts over a distance on an object, and it results in some form of energy transfer into or out of a certain system that you're considering. So the equation for that would be work equals some force over some distance. Now, it's important to note that that force is a force that is parallel to that displacement. So if we look at our equation sheet, you notice our equation sheet here has that cos theta there. That cos theta is important because if we had, for example, if you're pushing a shopping cart in a store, you usually don't push it perfectly horizontally. That looks kind of awkward, right? You probably push it on some downwards angle like this, and you push it across the floor, so our displacement vector would look like this. That theta is the angle between your force and displacement vector. So I mean, if force and displacement were perfectly parallel to each other, theta would be 0, and the cos of 0 is 1, and that sort of reduces to this equation you see here. Now the units of that are newtons times meters. But we give these units a special name. We call it a joule, after the British physicist James Joule. And that is the unit for work and all energies. Because remember, work is just a transfer of energy, so it has the same unit as any energy that we're going to calculate. Now, work and any energy we calculate are scalar quantities, so we don't need to worry about directions at all. Okay, and even though this is online, I can swear I hear you all cheering about that. Yep, no directions, so you don't need to worry about which way is positive. You don't need to worry about throwing negatives in. No, they're scalar quantities. Okay, so then when is work specifically done? Well, we need a couple things. One, we need a force to act on the object. And two, we need the object to change position as well. They both have to be done. I mean, you can go up to a brick wall and push on that brick wall as much as you want. Unless you actually get that brick wall to move, you've done no work, no matter how tired you actually get. Okay, and three, this one's a little tricky, but there has to be some component of force parallel to the direction of motion. So let me expand on that a little bit. Let's say, for example, that I was holding this pen, and I move my hand perfectly horizontal. In that case, if I were to draw this, the force on the pen that I apply is up. And I've moved it horizontal, so its displacement is horizontal. Those are perpendicular to each other. So there's no component of my applied force that's in the direction of displacement. So I have done no work. And that works in our equation too. If you put theta in as 90 degrees, the cos of 90 is 0, work equals 0. So this is what is required for work to be done. And because of this, we do get three different situations for work: positive, negative, and no work. So let's look at these examples. So this first example, here we have someone applying a forwards force on a stroller, and the stroller therefore moves forward. If that force is in the same direction as displacement, you get positive work. Okay, and I should specify that any force can do work. Okay, so in this case, there probably is a small frictional force being pushed backwards on the stroller. So what does frictional force do? So if we look at this last situation here, we have a stone, so we're curling, right? And it has a frictional force backwards or opposite to the direction that it's moving in. So you can think of that as, well, the angle between frictional force and displacement would be 180 degrees. Cos of 180 is -1. So that gives us negative work. Now look at the difference between positive and negative work, because we're going to talk about this in a little bit. When positive work is being done, you increase the speed of the object. When negative work is being done, you decrease the speed of the object. And kinetic energy has to do with the motion of the object. So work and kinetic energy do have a link that we're going to talk about in a bit. But first, our case of no work. So that's this case here. In this case, you're holding an object as you're on, it looks like skis, as you're just sliding across horizontally. Now, if we're looking at specifically this box that we're holding it and therefore applying an upwards force on the box. And if we're moving forward, those are at 90 degrees, so we are doing no work on the box. All right, so next, I want to talk about kinetic energy. So before I show you how work and kinetic energy are related, let's talk about kinetic energy first. So kinetic energy has to do with the motion of an object. Not only just its motion, but it's related to the object's speed squared. Notice how I specifically said speed and not velocity. Okay, because kinetic energy, just like work or any other form of energy, is a scalar quantity. We don't care about direction. Right? So if you wanted to calculate kinetic energy, here's the equation. It's 1/2 mass of the object times its speed squared. And work has to do with kinetic energy in a very specific way. And I've written it here, although I should specify. Let me zoom in here. I should specify that the total work acting on an object is the change in its kinetic energy. So what do I mean by total work? Let's say you start pushing something across the surface. Now, if that's the only force acting on the object, so zero friction, then as you push it, if you can continue to apply that same force, it'll continue to increase its kinetic energy. You can figure that out from Newton's second law. Your force causes it to accelerate, and so it goes faster and faster and faster. So it gets more and more and more kinetic energy. Friction does the opposite. If you were to stop pushing something, friction would take away that kinetic energy because friction does negative work. But what if you were applying a force and there is an equal and opposite force of friction? So let's say you're pushing a box across the floor and it's moving at a constant velocity. We know that if it's moving at a constant velocity from our free body diagrams, that your applied force and the frictional force must be equal and opposite, therefore there's no acceleration. Well, both you and the force of friction do work. You're doing positive work, friction is doing negative work. And because those forces are equal and opposite, the work done, the positive work, has the same magnitude as the negative work, but they simply add to zero. So the total work done is zero, and of course, your change in kinetic energy, there would be no change because it's maintaining its motion. It's not increasing or decreasing its speed. Okay, so there's that deep connection between the work being done and the kinetic energy of the object. Okay, so we're going to try some problems. Our first problem is just like our picture from the previous page. A mother pushes a stroller along the sidewalk. So let's say she exerts a horizontal force, so she's pushing it horizontally, not downwards at an angle. It's a big stroller, so it comes up pretty high. Horizontal force of 123 newtons. So we have an applied force of 123 newtons. As the stroller moves 42.5 meters, and so it's moving in that same direction. So our displacement is 42.5 meters. Calculate the work done. So the work is force times displacement, and just the magnitude, times the cos of the angle between them. Now, since they're parallel and in the same direction, that's cos of 0, and cos of 0 is just 1. So it just equals force times displacement, so we can write that in. So 123 newtons times 42.5 meters, and we'll get our work done. So 123 times 42.5. Okay, and you get 5,227, but keeping significant digits, 3 and 3, so 5.23. All right, in scientific notation, times 10 to the 3, and our units, joules. Make sure you have newtons and meters here. All right, as long as you have a standard base SI units up here, you'll get joules in your end. So the next question says, a large curling stone, mass 20 kilograms, slides along the ice at 2 meters per second squared. Part A says, what is the kinetic energy? Well, kinetic energy, if we look at our equation, is 1/2 mass times speed squared. Which gives us, again, put it in standard international units, so SI units, so it's in kilograms. speed should be meters per second, which is good. That's what they give it to us as, 2.0. And don't forget to square. That square is extremely important. So you get half times 20, which is 10, times 2 squared, which is 4, so 40 joules. Part B says, what is the speed of a small curling stone, so 10 kilograms, with the same kinetic energy? So if this curling stone also has a kinetic energy of 40 joules, let's use this equation. Same equation, but we're just going to rearrange to solve for its speed. So if I do that, I multiply both sides by 2 and divide by mass, and I'll get 2ek over m equals v squared. Take the square root of both sides, and we'll get v equals the square root of 2 times ek, which is 40 joules, all divided by mass, which is 10 kilograms. So that's 80 divided by 10, which is 8, which is 2 root 2 meters per second, but let's see what that is. Specifically 2.8 meters per second. Now, a really interesting thing which we're going to use in question 3 is we're going to combine work and kinetic energy, and it has some serious impacts. So let's just look at this problem. A roller coaster train moving at 8.15 meters per second glides to rest over 19.2 meters along the final horizontal stretch. So we have a horizontal stretch. Let's draw what's happening. Here's your cart. It's moving horizontally. So we have some displacement in this direction. Okay. And it's coming to a stop. So we have some sort of frictional force acting on it. So we have some kind of frictional force, kinetic friction. We know the mass of the train, so it has some mass. And we know eventually it comes to a stop. So what we're going to do is determine that braking force. And the braking force is our kinetic friction. So how do we do that? Well, we're going to use this work equals the change in kinetic energy. And specifically total work, but in this case there's only one force acting on it. So the only force that's doing work is our braking force. And it's going to be our braking force. If you want, you can call it FB. I've already written it as FK. So times displacement times the cos of the angle between those two vectors, which equals change in kinetic energy. So change is always written as final minus initial. We've done that a lot before. So in this case, I will write 1/2 mass times final speed squared. I don't need to write initial or final mass because the mass isn't changing. What's changing is the speed itself. Minus 1/2 mass times initial speed squared. Okay. Now there are a couple things that we can look at here. One, theta is 180 degrees. They're opposite to each other. So the cos of that is -1. Also, we come to a stop. So we know final velocity is 0, meaning our final kinetic energy is also 0. So this gives us negative, because of that cos of 180, Fk times delta D equals negative 1/2 mvi squared. Now both sides have a negative, so we can sort of get rid of those or multiply both sides by -1. And then if we're trying to find Fk, we just divide by displacement. So Fk will equal mvi squared, and 1/2 can be written as over 2, and then divide both sides by displacement. So now we can start putting everything in there. So mass is 1,490 kilograms. Its initial velocity Determine the braking force is 8.15. There it is. Don't forget to square it. I usually find lots of students forget to square. All divided by 2 times the total displacement that it undergoes, which was 19.2 meters. All right, put all of that in. We get braking force of 2,577 newtons. But again, I'll keep 3 significant digits, so 2.58 times 10 to the 3 newtons. Remember, force is always in newtons. So one thing I wanted to talk about is a question like this, but the fact that work, right, some force due to work is related to kinetic energy, which is related to speed squared. That's really important. So what this actually means is, let's say you're driving in your car and you're driving at 20 kilometers per hour. Now, if you were to hit the brakes and come to a stop, let's say you stop over a distance of 10 meters. We'll choose nice numbers. So you're driving at 20 kilometers per hour, you slam on the brakes, it takes you 10 meters to come to a complete stop. All right, well now let's say you triple your speed and you drive at 60 kilometers per hour. If you slam on your brakes to come to a stop, it's not going to take 3 times the distance, in this case 30 meters. It's going to take you 9 times the distance to come to a stop. So it's going to take 90 meters to come to a stop because it's related to speed squared. So you triple your speed, your stopping distance is by a factor of 9. If you double your speed, your stopping distance is by a factor of that doubled squared, or 4. Right? Which is something very, very important to know, right? Especially when you're driving. Don't always think that you can come to a stop immediately, right? You double your speed, you quadruple your stopping distance. So be safe.